Good morning. My name is Robert Ferguson. I'm a PhD candidate at the University of Texas at El Paso, and I will be discussing combustion of aqueous Han methanol propellants at high pressures. Several green monopropellants are based on hydroxyl ammonium nitrate, or Han. Han is an ionic liquid which decomposes exothermically at about 150 degrees Celsius. While it could be used as a monopropellant in itself, it is usually combined with a fuel additive to increase the ISP. Some examples of fuel additives include triethylenol ammonium nitrate, hydroxyethyl hydrazinium nitrate, glycine, and methanol, which is the fuel component of SHP-163 monopropellant, which has been studied in Japan. Han-based monopropellants combine low toxicity, particularly when compared to hydrazine, and high performance characteristics, most notably when accounting for density-specific impulse. However, the combustion of Han methanol water propellants at high pressures is not well understood. Some background research on this, starting with Kuo's team at Penn State. They studied two formulations of Han methanol water propellants at pressures up to 7 megapascals. Their formulations were identical except for the water content, so the Han ammonium nitrate and methanol ratios were exactly the same in both. Looking at the top line in the chart on the right here, we can see that this particular formulation produced approximately 5 different burning regimes over the tested pressures, including a particularly large jump at around 1.1 megapascals and a negative pressure exponent beyond about 3 megapascals. It's also interesting to note that the formulation that had less water only had 2 pressure regimes, both with a positive pressure exponent. However, the burning rates were lower over the tested pressure range, suggesting that water may play a role in the combustion of these propellants. Some additional tests were conducted by Peterson's team at Texas A&M. They tested at pressures up to 22 megapascals using both 82.4 weight percent aqueous Han solution and a solution of 70.1 weight percent Han, 14.9 weight percent methanol, and 15 weight percent water. For the 82 weight percent aqueous solution, shown in the blue line here, they found 2 pressure regimes, including a rapid increase in the burning rate at low pressures, followed by a negative pressure exponent beyond about 5 megapascals. With the addition of the methanol, they found a great increase in the burning rate at lower pressures, followed by 5 distinct pressure regimes as the pressure increased up to the maximum tested of 22 megapascals. Briefly discussing the reaction mechanism of Han decomposition. On the right, we can see a more complicated analysis of the decomposition mechanisms. However, we focus on the right for a second. Generally agreed upon overall reaction mechanism starts with a proton transfer, creating hydroxylamine and nitric acid, and then from there the nitric acid plays an autocatalysis role throughout most of the rest of the decomposition. This indicates that the nitric acid plays a significant role in the decomposition process, which we'll get more into later. Some studies that we've done at UTEP include atmospheric pressure thermogravimetric analysis and differential scanning calorimetry of aqueous Han solutions. Some examples of our tests are seen in the charts on the right with the TGA on top, DSC on the bottom. We determined a apparent activation energy of 62.2 kilojoules per kilomole based on the TGA data and 57.5 kilojoules per kilomole based on the DSC data. Combined with simultaneous mass spectrometry, during these tests we identified the major gas products as water, nitrogen gas, nitric oxide, nitrogen dioxide, nitrous oxide, and nitric acid. So the objectives of the current study are to clarify the combustion mechanisms of Han methanol water mixtures at high pressures, and we intend to do this by using differential scanning calorimetry of aqueous Han solutions at pressures up to 15 megapascals, combined with strand burner experiments with the mixtures including methanol at pressures up to 30 megapascals. The propellant blends we used, we ordered aqueous Han solution as a 24 weight % solution from Sigma Aldrich. For the HPDSC testing, it was used as received. And for the Han methanol propellants, the concentration of Han was increased up to 82.4 weight % by water evaporation in a vacuum desiccator. The anhydrous methanol was from Millipore, and that was also used as received in the propellant blends. The final propellant mixture is the same as that used in the McCown-Peterson investigation, which is 70.1 weight % Han, 15 weight % water, and 14.9 weight % methanol. Our high pressure DSC is a Netsch DSC 204 HP Pegasus. Again, we use the 24 weight % aqueous Han solution from Sigma Aldrich as received. In this case, a 10 microliter sample was placed into a 6 mm aluminum crucible. We used 3 vacuum cycles and then purged with nitrogen. 1 to purge the residual air from the furnace, and 2 to evaporate most, if not all, of the water from the Han solution. For the test we'll be discussing here today, we used a constant heating rate of 10 Kelvin per minute, and testing was conducted up to 15 megapascals, which is the maximum pressure allowable with the instrument. This is our strand burner. In the middle you can see the test cell. The gas rack is to the right, and on the left you see the control console where the operations are conducted. It was designed and installed by Design Integrated Technologies. It can operate at pressures up to about 5,000 psi or 34 megapascals. It uses a nitrogen environment, and a temperature bath controls the initial temperature to approximately 25 degrees Celsius. Because the strand burner was originally intended for use with solid propellant strands, we used a quartz tube attached to the test head to hold the liquid samples. The tube is 7 millimeters inner diameter and 9 millimeters outer diameter. 3 sets of holes were drilled through the tube, the first being for the nichrome ignition wire, and the second 2, placed 3.5 inches apart, are used for the 2 braking fuse wires. As these break in sequence as the combustion front travels, the breaking of the wires automatically starts and stops the timer on the control console, so we can determine the burning rate based on the time and the known distance between the 2 wires. Moving on to some of our results, this is the high pressure DSC testing. What we found here was that at lower pressures up to about 2 megapascals, we noticed a drop in the decomposition temperature by about 50 degrees as the pressure increased, whereas once we got past about 2 megapascals, we found that the decomposition temperature remained nearly constant. We associated this with the boiling point of nitric acid, which is demonstrated in the red line that you can see on the chart here. And what we think is happening is that below about 2 megapascals or so, the nitric acid that's produced from that initial proton transfer is evaporating, so it doesn't play that much of a role in the further decomposition until it builds up enough. Once we get past about 2 megapascals, the boiling point of nitric acid becomes higher than the decomposition temperature. Therefore, the nitric acid stays around longer, and the decomposition temperature becomes more constant after that. If you look in the bottom left, there's a couple of examples of the DSC curves that we got from these. On the left is 0.2 megapascals, and on the right is 8.1 megapascals. You can see a higher and more narrow peak at the higher pressures, which we consistently found through our testing. Moving on to the combustion experiments in the strand burner. The green line represents the Chang paper from Penn State, the red line the McCown-Peterson paper from Texas A&M, and the blue lines and the black dots up towards the top right represent the data from the present study. We tested from 8 megapascals up to 30 megapascals. At 8 megapascals, there did appear to be propagation of the combustion front, but it was apparently not hot enough to burn through to break the fuse wires. We checked some DSC testing on the fuse wire material and found that they break at around 318 degrees Celsius. So this indicates that the combustion temperature at 8 megapascals was approximately was likely lower than that. Above 9 megapascals, we consistently had the fuse wires breaking and were able to produce consistent data. I would like to point out our data is distinctly higher than that from the McCowan-Peterson results. We believe this is associated with the direct data from the breaking of the fuse wires and the timer, whereas in the McCowan-Peterson results, they used pressure-based data which included gas phase reactions, leading to a longer burn time and thus producing apparent slower burning rates. Continuing on with the combustion studies, we can see approximately 4 distinct burning regimes as the pressure increased. We have an early negative pressure exponent at the low end of the pressures of approximately negative 0.75, a very noisy region from 12 to 14 with the large error bars you see there. Then we see a plateau from about 14 up to about 19 or so megapascals, a bit of a drop there, and then once we get to about 22 megapascals, a fairly consistent exponential increase in the burning rate with increased pressure from there of about 1.35. I'd like to point out that the critical pressure of water is of course 22 megapascals, which is about where we start seeing that consistent burning increase at the end. As we saw with the HPDSC testing, there was no pressure effect on the Hahn decomposition observed, so we eliminated that as a likely cause of the various burning regimes we see here. However, I would like to focus on the abrupt increase we see at about 12 to 14 megapascals, where the very noisy region with the large error bars are. So right there, we believe we're seeing a transition to a faster combustion regime. And if we specifically look in at the actual test results, we see that some of the test results seem to line up with the lower pressure negative pressure exponent, whereas other tests seem to fall more in line with the plateau that we see at higher pressures. This seems to indicate that there's a transition region going on right here. So we calculated the pseudocritical points of Hahn water methanol and water methanol mixtures using the Prausnitz's gun expressions that you see here. And if you look at the chart on the right, we see that the critical pressures for Hahn water methanol mixtures was estimated to be about 10.5 megapascals, whereas for water methanol was about 14.5 megapascals. Now, neither one of these include the decomposition products of Hahn as well, but the pressures are in line with right around where we're seeing that transition region. So what we propose is happening is that below this mixture pseudocritical point, the Hahn is decomposing and producing bubbles in a liquid. Because of the liquid's boiling point, the temperature of this combustion front at the liquid gas interface is restricted and unable to exceed that boiling point. This is essentially putting the brakes on the burning rate or the reaction rate. In addition, as the pressure increased, it has been reported before that the meniscus becomes shallower, thus decreasing the surface area at the liquid gas interface and therefore reducing the amount of decomposition from there. Once we get past the pseudocritical point, the Hahn is decomposing within a supercritical fluid. At this point, there's no longer a boiling point which is restraining the temperature, and the reactions are able to proceed much faster. In conclusion, the DSC did not show any pressure effect on the Hahn decomposition at pressures above 2 megapascals. We found that the combustion of Hahn water and methanol mixtures exhibits 4 distinct pressure regimes in the tested range of 9 to 30 megapascals, and the sharp transition to a faster combustion regime in that noisy region at 12 to 14 megapascals can be explained by supercritical fluid effects. I'd like to acknowledge the Air Force Office of Scientific Research Space Propulsion Power Program for their support of this project. Thank you very much for your time, and at this time I'll take any questions.